Creo que vamos a empezar a emitir la...
Yeah, we are live. We are live in YouTube. Welcome to the IPARCOS-UCM.
Okay. So, good morning, everyone. Welcome to our IPARCOS seminar. Today we have the pleasure to have with us Dr. Álvaro Hacar from the University of Vienna. Álvaro received his PhD here at the UCM in 2013. And he then moved to Vienna as an assistant postdoc until 2016. He then moved to Leiden until 2019 as a new Beni postdoctoral fellow within the Netherlands Organization for Scientific Research Program. Between 2019 and 2020, he was all the support scientist within the ALMA node in Leiden. And he returned to Vienna as an assistant professor at the Institute of Astrophysics, and recently he has been promoted to associate professor. His research is devoted to the study of the early phase of formation molecular clouds, and today he will talk about how massive stars form. So thank you very much, Álvaro. The floor is yours.
Yeah, thank you. Thank you for the introduction. Thank you for everybody being here and for those online. I have to confess that this is a really special talk for me. First, because I was not here in the last 10 years or so. And because, as Enrica mentioned, I basically spent a non-insignificant part of my life in this faculty. So I will talk a bit about my research recently, particularly after I left the UCM. But all of this started as part of, let's see, this moves. No, does it work? Doesn't work. So as we are here, just a short CV, and as you see, I mean, here, this is my alma mater. I've been on the other side of this room, sitting in these chairs. I mean, not in these chairs, much older chairs. But I did my studies up to the master's, and then I graduated here as PhD at the USM. So it's really close to my heart to be here back. And you see here me in the trabajo académicamente dirigido with Jaime Zamorano, who I deeply thank Jaime that you are online today. And you see me here, I mean, 20 years younger, also 20 kilos lighter probably back then. So the important thing, and this is what I also wanted to share with the students, is that, I mean, I've been through everything you are now going through now. And in particular, I was part of the first master's degree at this faculty. Here you have a picture back in the days at the Calaralto Observatory, the first visit, and then you see, I mean, some people that might sound look familiar. Actually, they are here in the audience, they are laughing now here. Again, all of us a bit younger, and then you see what we try to do with the South Park character. So it's again was a great experience being here. I learned a lot. Yeah, we were the first of the new generation of masters. That back in the days there was no master study. So because of that, I just wanted to show you that. So I've seen things that you people will not believe. So I've seen, joint masters between two universities. I've seen all professors here teaching, let's say, in the old style. But of course, I've seen many great things. So that was also a great experience. And I have, for instance, one of them is here in the audience. So that has been a great experience. And there is also light after that. So don't worry, you should go ahead and then keep going, keep pushing. So what I'm doing now is, so after my studies and for my PhD, I started my work as a radio astronomer, in particular observation of the interstellar medium. And now I'm working with radio telescopes like ALMA, and APEX, and IRAM, studying the molecular universe. And what I'm doing with this is to investigate the early stages of star formation and the ISM structure. Here you have one beautiful image we got with APEX, La Boca instrument at the APEX telescope. This is, you see this long filament that you see here is the core of my studies. And this is, as I will explain you now, how stars are formed. Just a brief remark, I went back to the archive and I checked who was back in the days the observer of this telescope. You know, the apex is done in service mode, and maybe somebody here in the audience can tell me who was observing, right? You recognize both, right? So Paco here in the audience, he recognized himself. That was you, right? And the other one is my wife. Okay, so you see, everything here is a family. Everything here, you know, we are in a really close world. So if you start here, the people you see around, you will keep finding them over and over, and it's a great pleasure. So this is my studies right now, and this is what I wanted to present you today. So I'm trying to address one of the fundamental questions for star formation, and actually for astrophysics in general, which is actually sometimes referred to as the holy grail of star formation, which is the origin of the initial mass function. Initial mass function defines, if you take a volume of space, where galaxy, for instance, you count the mass of the stars in there, defines what is the specific mass distribution of these groups of stars. And it's surprisingly homogeneous. I will not say invariant, but I would say surprisingly homogeneous. And you always have, I mean, most of the stars are typically low mass stars are called, so stars similar or slightly less massive than our own sun. And this distribution is followed by a power law tail of what is called high mass stars, so stars more massive than our own sun. This unique distribution is fundamental for our understanding of the universe. It defines the evolution of entire baryonic matter. It tells you how many, so where is the mass? The mass is in the low mass stars. How many of the more massive stars you form, and therefore how many photons you produce, what is the chemical and energetic distribution or evolution, sorry, of the universe, just by this unique initial mass function functional distribution. The problem is that even when it's so robust and universal, if you go to you took Jaime's courses, for instance, and many others on star formation, including all textbooks, will tell you there are two ways to form stars, actually two modes. So you have a mode for the formation of low mass stars. Low mass stars form in a quiescent environment, typically slowly, more or less in isolation, and you can find them in regions like Taurus, while high mass stars almost uniquely form in clusters, so in groups of large number of objects, in a really rapid way and in a really harsh environment of radiation. So this separates these two modes, and people call them the low and high mass star formation modes. So the question here is that, is this true? And if so, why you can reproduce then always the initial mass function? Or we can actually connect the two. So that's the big question. Something we have learned, and this is, for instance, a slide that I presented for my thesis here for the first time, so coming back more than 10 years after. So this is the standard mode for low mass star formation. So you have a low mass star, similar to our sun, that is embedded in what is called a dense core of gas, a sphere of gas that eventually collapses under its own gravity. And these cores and low mass stars form typically in little groups of 3-4 stars. But if you see carefully, they are connected by emission that basically continues later on in these really long filaments of gas. Filaments that can be as large as several parsecs. And then these filaments dominate the cloud structure of regions like Taurus. Okay. Okay. Oh, sorry. Okay, so maybe we need to sacrifice our own screens here.
Yes.
Oh, no. Oh, no, it's okay. It's okay. It's okay. Maybe now this works. No, it doesn't work. Yeah, now it works. So what we have learned recently is that filaments play a key role in the formation of at least low mass stars. This has been done from studies like Herschel, when the Herschel Space Telescope observed nearby molecular clouds. What they found is the gas is heavily structured, the gas and the dust is heavily structured, even before you form your first stars. So here you have a molecular cloud, and you see that the gas, which is now traced in these colors, is basically forming these elongated structures. And the protostars, the new young-born stars, are always on top of these filaments. So that allows us to create kind of a standard model, in quotes, about how low mass stars should form. And this is basically a fragmentation process. You create first one of these filaments, and then you fragment them in pieces, and each of these pieces then evolves independently, and you form stuff. You can work out actually the analytics of this. You can do it with pen and paper, and then calculate what is the expected mass for one of these cores. You can do this assuming, actually a condition that you need is that the filament is originally stable, gravitationally stable, and then you perturb these filaments, and if you do this with the right mode, then you fragment your filament in chunks of few solar masses, and each of these solar masses, each of these cores now then collapse and form a single low mass star. So that's easy. We know this and we understand it. The problem of this explanation is that also sets an upper limit on which is the more massive star that you can form in this way. And this is because in order to achieve the first condition, you can have a maximum of mass per unit length. This is the way we define the stability of these filamentary and cylindrical geometries is by how many solar masses per parsec you can have to be stable. And this is the only number that I want you to remember, on the order of 20 solar masses per parsec. If you are in these conditions, then you are ready to fragment and form stars. Then you produce these fragmentation modes, and then that's sent up into these values. The issue then is that you cannot form a more massive core than this. And therefore, you cannot form high mass stars in this way. It's physically impossible. You will need to increase the mass, but then your object is unstable, and then you will collapse radially before you fragment. So you cannot form high mass stars in this way. Because of that, so this sets an upper limit of your mass. Because of that, people created different models for the formation of high mass stars. And I mean, there are many details that I'm not going to discuss here, but one simple model is what is called a turbulent core. So it's the same idea that you create a big core at the beginning that is much larger than these low mass cores. And this is sustained by a really high turbulence inside. So you can, this produces some extra pressure, and then you can hold it until you accumulate enough mass to collapse. This is one way. So you start with a really unstable situation. And the other one is that you have a competitive accretion where you have different fragments that each one starts accreting locally. And here, rich get richer. So the more massive, initially more massive cores accrete faster, and then they grow faster and they are these massive stars. The problem of these two modes, and these are the standard ones assumed in the literature, is that people have been looking for these initial conditions for decades. So people have spent hundreds of telescope hours looking for these precursors of high mass star conditions, and we couldn't find them. So they do not exist. Whenever you observe things that look initially like a big clump, you observe at a high resolution and then breaks down in pieces. So the question is obvious: are we doing something wrong, or can we say something better than this? And this is where ALMA came into play, where we can now, for the first time, observe high mass star forming environments really far in the galaxy, because they are usually not close to us. And then what we found something interesting is that here you have an example of two high mass stars, meaning 40 solar mass stars, so they are really big guys here already. And they are formed not directly in the filaments, but connected to them. So you see that there are different filaments that you indicated here, but you see the image there. They are these high mass stars, the new high mass stars, are formed at the junctions of different filaments, at what is called hub filament systems. And so this is telling us that there is some connection with the formation of filaments, but not exactly the same as what we saw for the low mass case. So the question is, can we say something on this line? These have been observed everywhere, so this is not just one case. Here you have one of the beautiful star-forming regions, high mass star-forming regions in our galaxy, observed by Herschel. And then you see that, again, you see the bubbles here created by the high mass stars. These bubbles are already, you see the filaments everywhere. So the ISM is strongly filamentary by construction, and it's necessary to produce the structure that we see. So we need to connect these two things, how low and high mass stars are formed in connection with these filamentary networks. But because what I said before, again, there are many open questions in the field right now. So for instance, I just show you a really simple example of how we think filaments fragment, but the physics behind that is probably a bit more complex. So how do these filaments actually fragment? This is not just a stick that fragments into pieces, so there are a bit more subtle differences here. The second is that I've been talking about filaments as this is a unique thing, but this is not guaranteed. That is that the filaments that you see here, these are parsecs on scale. Sometimes you have much smaller filaments. So are they all the same? And are they all, so we can interpret them in the same way? And as I said, the cherry on the cake is that if somebody can answer the question that whether these formation mechanisms for low and high mass stars are the same. And this is what we are trying to do. How do we do that? Well, I'm, as I said, a radio astronomer, and I'm working with sub-millimeter molecular lines, so molecular lines observed at the sub-millimeter. Why is this advantage compared to other techniques? Is because, so here you have on the left, you have a molecular line emission, which has a kind of a relatively simple Gaussian shape. The important thing to realize is that this relatively simple observation carries the physics of the ISM in many, many ways. And this is because you can connect this shape, the emission, and the properties of these observations via the relative transfer equation to the basically physics that generate this line. So this simple equation that can give you the profile, the peak, the width, is produced by a combination of the excitation of the line, so the physical conditions of how you form this line, density, temperature, abundances, and stuff. Some properties of the lines itself, because different lines of different molecules produce different lines, the column density and the chemistry along the line of sight, and the velocity field that produces this line. So it's intrinsically complex, but if you are able to disentangle these properties, then you are able to get a lot of information of the ISM and particularly over packets. In my case, I focus mainly, but not only, in the velocity field. I analyze the dynamics of the gas along the line of sight using these lines because of the component of the velocity field that we can investigate. And I know that the audience is not made of radio astronomers nor people interested much in astrochemistry, and I fully respect that. You should not do that. But I would like to highlight three molecules that we are using because one of the beauties of this, I'm not studying astrochemistry per se, but I'm using astrochemistry. So you can use different tracers to see different depths and different densities in your cloud. So for instance, just remember that if you see something observing CO, carbon monoxide, you are typically observing the diffuse gas of your clouds. And if you see things like nitrogen-rich molecules like N2H+, so you are going to see really high density gas, which is about to form stars. So with these two things, and knowing that you can do what we call molecular tomography. So you can observe the same region, use different tracers to see different structures, like you will see in a medical imaging technique. So remember these two things, the CO and N2H+. Okay, so going back to my days as a student, that I started as, actually, everything started with my master thesis project, and then, of course, evolved into a more sophisticated PhD work. But then we started studying different filaments in nearby star forming regions. And our first target was what is called the Barnard 213 filament in the Taurus molecular cloud. This is one of the ideal cases defined by Herschel as star forming filament. So if we want to understand how low mass stars are formed, this is a great candidate. The problem here is that it's already challenging our knowledge, because you can calculate what is the mass per unit length of this object, and it's on the order of 50 solar masses per parsec. As I said, this number is twice the mass that you can have to be in equilibrium. So how on earth you can have something that is completely out of equilibrium, still visible, and still form stars? That's the first question. So this is continuum. You see the total column density on the line of sight. What we did instead is to investigate the molecular emission of this object. So this is the central part of here. And then you see different molecular observations in these dense and diffuse tracers. The first thing that you can notice is that there are some regions where you have one velocity component, both in the dense and diffuse gas, meaning that you have one object there with different density, right? But the interesting thing of this region is that you move around and then you start finding regions with two velocity components, sometimes dense, sometimes diffuse. The velocity components shift in velocity, they change in intensity. Sometimes you have two peaks, sometimes you have three peaks sometimes you have 4 peaks. And sometimes, like in this super extreme case, you have 5 velocity components along the line of sight. You have 5 different velocity structures superposed along the line of sight. So what we did, and that was my thesis work basically back in the days, was to investigate it. We have, I think at the time, almost 30,000 spectra. We decompose them, we study each component individually, and then we put them in an analysis that I would just briefly explain because it will make you understand the rest, in what is called the position velocity space. So each of these velocity, the Gaussian, each of these velocity components you see that we fitted with a Gaussian, you can place them in this space by the position of the spectrum, position, and the centroid velocity of your line. And then you can see that this relatively or apparently complex structure in velocity is actually quite organized in space as well. So you see different components at different positions and different velocities, telling you that there are many structures together in there. And my thesis was to how to identify and reconstruct this with some algorithms. Why is this important? Well, let's go back to the Herschel image. So this is the Herschel image of this Taurus filament, the central part. Here you see these little clumps that are the seeds for low mass stars, and then you see the long filament. But already in Herschel, you start seeing some really subtle things, right? So, okay, might be some kind of large-scale structure there, but there are some hairs coming out of this. These structures sometimes forks, sometimes connects again. You have this here everywhere. So something that looks apparently simple at low resolution and column density is actually quite complex in kinematics, and you follow these things. You can demonstrate that this apparently unique structure in continuum is actually a collection of what we call fibers. We call them fibers because it's like a rope made of small-scale twisted things, but you can think about this as sub-filaments of sizes of a half of a parsec each. And then you basically put them together, and then you create this large-scale structure. So there is a hierarchy of these objects, first of all. And why it's interesting is that once you have these fibers, sub-filaments, or whatever you want to call them, these objects are close to gravitational equilibrium, and they are really quiescent. So they are exactly in the conditions that you need to then form and fragment. So fragment these filaments and then form your low mass stars. So there's a necessary step in this process to go from the large scale structure to then to the small scale fibers, filament, or whatever you want to call them. And then there's where you have the conditions to the formation of the formation of low mass stars. Then you can fragment quiescently, then you can form your YSO, your young stellar objects by pure, slow, and quasi-static fragmentation. So that was great. That was important because then for the first time we can understand how the gas structured right before you form your stars. And fibers appear as as a necessary step in this process, cascading from the large scale to the small scale. So this is interesting, and I mean, I was really happy that was my core result for the thesis. But of course, I mean, let's go back. So this is Taurus. Taurus is a really beautiful, I love this star-forming region, but if you ask anybody, particularly in the extragalactic community, what Taurus looks like in another galaxy, they basically don't see it because it's so tiny and it's forming very few stars that it's completely relevant for the large-scale picture of star formation. We learned a lot, as you see from it, but in the global picture, it's less relevant. So what is important in this case is the formation of clusters, regions forming clusters, regions forming high mass stars. The large molecular clouds that then dominate the star formation in galaxies, and actually those that you can actually see later in the extragalactic context. So the nearest cluster that we know is the Orion Nebula cluster that you can see by naked eye on the sky, forming the trapezium stars. Already you have O stars, you have a really massive object in there. And this cluster is known to be associated to a really long, you almost see it here in the infrared image, a really long filament that crosses this cluster. So the question is, again, is this connected to the formation of the cluster itself or not? And then we face the same problem as before, actually much worse. So if you calculate the mass unit length of this huge structure, what you find is that your mass is on the order of 40 times what you can have in equilibrium. So this object should not exist. This object should collapse into a single spindle before even fragments to form any single star. So the free fall time is so fast that you will not fragment. So the question is, how is this possible? And for that, you need to already go to ALMA because it's already almost it's 400 parsecs away. You need high resolution to resolve this. Before I show you what is the ALMA result, I would like to show you what people thought about this region before. So we go, actually, the time of my thesis, now I was about to say 20 years ago, but it's almost. When people observe this region already in the past many times with low resolution telescopes. So here you don't see now because it's the radio image, but here you have the cluster, you have the trapezium, you have the Orion BNKL, the new high-mass star. So the cluster is down here on this corbel. And if you observe this region in tracers like N2S+, the dense gas that is about to form stars, then you see that there's this long structure, and you start finding some clumps here. These clumps are where the new high and intermediate mass stars are being formed right now. And you look at the spectrum, and I mean, you don't look at this side. This is the hyperfine structure of the line, doesn't matter. You look at this component here, and you measure the width, and this is a supersonic line. It's a line that contains a lot of turbulence, and basically that's the origin of this theory that I mentioned before. So clumpy things with really broad lines, supersonic lines. So okay, we are fine. Why in these theories or where observations fit the theory? The problem here is that we are observing at really low resolution. So what happens when Herschel came into play? Well, you can improve a bit the resolution, and then you start finding something interesting that your roundish clumps start not being roundish. So that's surprising because then you break already the assumptions at the beginning. You start having these little fragmentation or fragments or forks or whatever you want to call them around them, and look at what happened with the molecular lines that you observe. So your broad line that look unique all of a sudden splits in two. So okay, we are still safe in the sense that these are still supersonic. I mean, we call them transonic. You are at the edge of sonic or transonic lines, but now you have two structures. So that's confusing. We are still 10 times in low end resolution compared to ALMA. So when you observe the same region with the ALMA resolution, you move from this picture to this picture. So your picture is no longer clumpy anymore. So you see that the original blobs are now a really complex network of small-scale filaments everywhere. I mean, it's not just one region, it's all of them. Sometimes they merge, sometimes they fork, sometimes they do a lot of things. And I mean, a complexity that's even hard to describe at this point. More important, look at the broad line initially is now three narrow lines together. So there is no such supersonic gas that maintains the whole structure, at least not as a unique line. But then you have a lot of superposition of structures, and this is what later gives you this idea of broad lines. But your gas is heavily structured from the beginning, even in high mass star forming regions. So we did the same analysis. So we used our algorithm, and then what we found is that this, again, unique structure that was already defined in the past is now a collection of dozens, I mean, in this case, more than 50 substructures, all of them, I mean, much tinier, much smaller, and then that they satisfy these conditions of stability, both in mass and dynamics in terms of line width. So the gas, also in high mass star forming regions, is heavily structured in these tiny filaments, and that is actually what you need. So it's not surprising because you need these conditions to form your low mass stars. You need these quiescent in quotes, filaments to be able to fragment into tiny fragments of the size of the sun, right? So when you observe with enough resolution, you do not have these turbulent motions anymore, and you have these collections of these little. Just to prove that, I mean, just zooming in a couple of these regions. So now there's the same data, but much smaller. So look at this. Let's go back here. So this one here, right, in more resolution. The crosses that you have here. So this is the structure. You see the filaments everywhere. The crosses that you see here on top are the identified low mass stars being formed right now. So it's a compact continuum objects that are basically the seeds of low mass stars. And you see that this long structure is like is full of these tiny little stars, right? Because now you are promoting the formation of these objects. So that's great. What is the difference then? So what happens? Why then you have a big cluster in Orion compared to few distributed stars in Taurus? So how this is happening? Well, one key ingredient, sorry, is the density. the density where you find these things. So here you have a chain of cores, one of these fibers in Taurus, and you have the same scale and same size now in Orion. So forming both low mass stars, both having quiescent filaments, both fragmenting into objects. But look at the size of these things. So the same region that is forming 3 stars here is really big in Taurus and is tiny in Orion. You have your gas is originally already much denser, and that's one of the game changers here. So you have the same physical process. You have this fragmentation from large scales to small scales into filaments within filaments. But then some region like Orion, they manage to do that at a much higher density, and that explains why you have the distance between your objects as much smaller. You can pack many more of these objects together, and you have a lot of mass to do that, so you have a lot of these objects. And second, the main difference here is that because you start already from a really high density, your rate, so the speed in which you form these stars is already much higher. It's already accelerated from the beginning, because you can calculate this by hand from the free fall time. So the free fall time of this guy, 2 orders of magnitude denser than this guy, is already a factor of 10 at least faster. So you form it's the same physical process, but at different densities. So at least for the low mass stars, this seems to be the case. So then what happens? Well, then there's another problem. It's like, okay, yes, you form stars in the same way, but how do you form more stars? So same process, yes, same density, how do you form more? Well, we came up with an idea, which is that you remember I was measuring the mass of the large scale structure as mass per unit length. The mass, how many solar masses you have in a given size, and actually kind of a volume. And then now we can count how many fibers, star-forming fibers, we call them fertile fibers, in this region. And if you do this with the different objects that you can find, we did this study in the past in the same way, then you find a linear correlation. It's of course, it's subject of many observational biases, so I'm not claiming that this is a completely linear, but there is some correlation between the super low mass star-forming regions like Taurus and Musca, intermediate mass clusters like NGC 1333, and high mass star-forming regions like the Orion Nebula cluster in the integral shape filament. There is a connection between them based on how many of these objects you form to form low mass stars. More fragments, more fibers from the beginning will lead into more stars. And the interesting thing is that then there is no such a distinction anymore between what you call isolated star formation and cluster star formation, or between low mass star formation and high mass star formation. It's just a continuum. It's that you put more, you get more. Your process speeds up as well, but then you get the same. So for the first time, we can start thinking about a single process to produce both low and high mass, isolated and cluster. Just depending on, and this is an external process probably created by galactic processes like spiral arms or similar. You manage to put all these gas together, and then the process then starts. Fragments really quickly, fragments down to the subsonic level, and this happens in these elongated things, and then you fragment them, and then you form your low mass stars. You have more of those, you have more stars. You have few, you have isolated star formation, you manage to put all of them together, or many of them together, sorry, and then you form a cluster. So it's the same process, just scale up. So you keep the properties of these fibers, and then you make them smaller, you make them narrower, and then you increase the density, and this is how you trigger these different modes. And they are not modes, it's a continuum of things. So the next question is then, because I'm cheating, I was cheating until now. I was showing you how low mass stars are formed, but I didn't tell you how high mass stars are formed. So that's the key, right? Because up to this is just more low mass stars. So what changes? What makes a high mass star? Is it still different? Well, maybe the answer is the connection with the system as a whole. Here you have now the same star forming region, so the integral shape filament Orion, the cluster at the center. You see in yellow is over the map that I just showed you, the ALMA map. And we map this also in low resolution, but much larger scales, right? In the same molecule, this dense tracer. But look what happened here. So you have the long filament, you have the cluster at the center, if you look at the velocity, this region is known to have a large scale gradient, so from more bluish velocities to reddish velocities. No, sorry, the other way, the blue here in the left, the right on the right. So this is known. But what happens when you get close to the cluster? So you see this zoop, zoop, this V-shaped profile. This profile that you see here in velocity is the line of sight velocity that we are seeing of the gas. This is an accelerated profile toward the center of gravity of the system. You can calculate that, and it's exactly this profile. So what happens, what makes a cluster, what makes a high mass star is that you have these same conditions, same physics for the formation of all stars. But when you reach a point where you put a lot of mass together, you have already your low mass stars available, cluster, the system becomes gravitationally unstable, the whole system, the whole region, and then it collapses towards the center, and this is how you form your cluster together, you bound your cluster, and then in some of these regions, then you get lucky. How you get lucky? Well, you see, so this is now the same image. This is our same, let's see, no. Those are the same ALMA map that you saw before, now tilted. Here you have now the trapezium cluster on the left. Here you have your fibers pointing towards this. So you create this gravitational focusing effect. That now you are funneling material into these hubs, just because of a property of the system. We call this the emergence of high mass stars. It's a process that was always there. You don't need any extra ingredient for that. It's that only when you have enough mass, then you trigger this global collapse. And this is what puts your mass together to form your high mass stars. And we see this now here. So the cluster, the nebula cluster is already off because this already happened for this cluster. And this material that you see the arrows tell you what is this happening, is collapsing here. This is the new high mass star in the region. This is the most compact clump we know in the solar neighborhood right now. This is the OMC1 South protocluster. So here you have, in this tiny region, you have on the order of 30 stars being formed right now. Because now your system is what creates your star. So that's the idea, that's the hypothesis. And then in these conditions, again, you generate the flow, you generate the mass inflow that you need for the stars, and then you start colliding these things. And that's basically, this is probably the only change that happens. Again, it's always there, it's just unlikely in other situations. But when you have this, you can collide, you can put a lot of material, and then you make really fast star formation. And that was actually the reason why I got this ESC grant to work in Vienna to basically explore these properties. I will just flash some results. We are using intensively now ALMA in the ALMA archive. And then we are now finally, after some years, where the first wave of paper will come in the next months. So what we are doing in this case now to extend this study, that this was just one region, I mean, a beautiful region, but just one. We want to do this across the galaxy. And then we started already with, so these are my two PhDs, Andrea and Francesca. And for instance, Andrea did already the analysis of 7 of these regions. So these are the 2 regions that you saw before, MC1 and 2. So this one is on top of this, you see the entire map. But then we extend this region to both low and high mass stars, star forming regions, exactly in the same way, same analysis. And there are a lot of technicalities that, for instance, Francesca is doing, so I will not talk about this, but how you combine the data and stuff. Sorry. But when you do that, and then you do the analysis, and then you do the same thing, you start finding that this process is basically happening everywhere. Low, high mass stars, low and high mass star forming regions, small clouds, large clouds. The gas is always structured in these tiny little, and I will not call them filaments anymore because it's a really bad word, but elongated features that then later fragment into stars. And then you see here the comparison of all of them. And then for the first time with this thing, we can do statistics, real statistics. So we can reproduce now this plot that you saw before, but now with many more clouds, now done all at the same resolution, at the same sensitivity, at the result, completely homogeneous. And then we start seeing other things, like when you then compare the population of objects that we recover, these fibers, now we have 150. And you then can do a statistical analysis, and you see that those that, because you have many that are forming, many that are not forming stars, those that are forming stars are what we call active objects, and this is because they are above the average in terms of gravity, so they are those that want to fragment. And you can do this statistically, and then you see populations, different populations. This is part of the analysis that we are doing now. So that's what the future will bring. And the other thing that we are going to do, and I will finish in a few minutes with this, is that you saw this map that I just showed here. We have these other regions around it and other parts of Orion. The important thing now is not only to understand these objects in isolation, is to know how they connect with the cloud. Because as I said, this is a fragmentation process from the large scale to the small scale. So how you then create the specific properties of these objects. Here you have this region, the MC3 region observed by Herschel, and you see a filament, okay, fine. You can do this with molecular lines at low resolution. So this was over, again, 20 years ago. What I just showed you a few minutes ago is when you move to this, from this to this. So this is the big change for ALMA, right? This is the dense gas forming stars. And you see the protostars are in these triangles, and then you see them again all over the place along these tiny little things. The important thing is to see what happens around them. So this is what Francesca is also doing now. Now you look at a slightly different tracer, now a bit more diffuse gas. You see that it's more extended. This is again what low resolution data are telling you. You can move to high resolution and then you find this. So we are now in a level of complexity that is really hard to describe. Actually, I cannot tell you how we will describe this because I have no idea. But you see that the dense structure that we are now filtering with this molecule is now connected to the cloud with really diffuse, I don't know how to call it, like whiskers, like a cat that has these whiskers around it. But this is basically how the mass is flowing into these dense regions. And this is what we want to study right now. So that's the future, and this is what we hopefully can show you in a few months from now, after the first wave. So I finish here with my summary conclusions. Before that, so I was, and I will go through them in a second, but I learned recently something really sad for me. And it's because so during my studies here, I had, actually during my whole research, I had several mentors, and always helped me a lot, and I recommend the students to have a mentor. I recently learned that unfortunately one of these mentors passed away. And I mean, I was working with him a lot. Maybe some students benefit from that work. I learned this because I invited him to come here today. His wife, unfortunately widow now, replied saying that he would not be able to make it. Anyway, so thank you, Enrique. Have a mentor, somebody can help you. It will have a big impact on you. Going back to the science, just to again summarize the few things that we discussed today. So I hope that you show and I convince you that there's a really important process on the fragmentation from the really diffuse gas to the densest gas that forms stars. We find this hierarchical structure of filament within filaments, and actually not too surprising, because I mean, we know for decades already that the ISM gas is fractal, meaning that you repeat the same structures over scales. And the interesting thing is that we find these fibers, and fiber just means that whatever elongated things that are already in this quiescent mode, so where you dissipate already all the turbulence of the gas, and then you have these conditions for the formation of fragmentation, formation of stars in both low and high mass star forming regions. So this is a connecting point of these two things. And what we think now is that this opens the new window on trying to connect these two modes that so far have been disconnected and so far treated differently. Maybe they are not that different. Maybe they are quite similar. And this is just what we call this emergence of high mass stars. The process is always there. The physics is always there. It's only that it's unlikely to form high mass stars in regions where you don't have enough mass, in regions where you do not have enough of these filaments that will collapse the system. If you believe in what I said, the formation of high mass stars and clusters comes for free in this new vision. So I stop here. If you want to know more, please visit our webpage, and I'm happy to take your questions here today.
Thank you very much, Álvaro. Time for questions. If you have, yes.
Yeah, maybe an easy question to ask and difficult to answer. What's the role of magnetic fields in all this?
Yeah, so I don't have an answer. Actually, I tried to escape from magnetic fields. They are really complicated. But it's definitely not. So once you have these super dense structures, let's go back to this. So once you have these super dense structures, probably magnetic field doesn't matter anymore, in a sense that this is already gravitationally dominated, no matter what you do here, right? So you're already on your runaway collapse here. What probably has a strong impact is in the diffuse gas. So you are more diffuse, you are more turbulent, and you are more ionized. So you are more prone to feel the magnetic influence. And some of these little things, so the magnetic field here goes like this, so perpendicular to it. And some filaments have the same property. So magnetic fields can, I will not say dominate the process, but can channel the gas into the dense regions and modulate this process. And there are both models and theories that predict changes depending on whether you have or not magnetic fields. So, but I usually avoid them for good.
So, but still without magnetic fields, you can explain fully the formation of these filaments.
Yeah, yeah. I mean, one difficulty on using the word filaments and talking about filaments in general is that all physical processes that are involved in star formation, so turbulence, gravity, magnetic fields, hydrodynamics in general, they all generate filaments in one way or another. It's because the physics is intrinsically anisotropic. So it's really easy to find some kind of pancakes, if you want to call it like that. The question is how to differentiate them. So you can find and form them with zero magnetic field, and you find slightly different ones if you include magnetic fields and depending on the strength of the magnetic field. So that's the tricky part. It's not, if you have this, then you can say they are magnetic field. No, it's really complex interface between them. It's which type you find and which are the conditions that you find.
I have curiosity. I was wondering, do you use any other high density gas tracers along with N2H plus? And why N2H plus?
Yeah. So N2H plus, first of all, is a well-established tracer in the first place. And it's because it's in the right, it's sensitive to the right gas in a sense that it's sensitive to the really extended gas. So still you see it in many parts of the cloud. Already differentiates from the diffuse gas, and this is because of a chemical process that happens in the gas. So the CO gas disappears from the gas phase at a given density, and then when you form this molecule, and this is why it's a really good tracer of the density. And it's bright and it's convenient also for observation. You can observe this in a much higher density tracer, and then what you will see is like basically blobs, little blobs here. Mm-hmm. But what we wanted to do is the connection between the large scale to the small scale. So this is why we are using it.
Any other tracer like HC3N or?
HC3N, so we have, so these cyanopolines, we actually have it in our study, and HC3N is sensitive to the feedback of the stars. So you see that like the popcorns in there. So you see these are the seeds, and then you see pop, 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 like the little gas around each protostar, which is heated up, and then you produce these cyanopolines, the HC3N. So in the cluster itself, and next to the ONC, the whole region is shining in HC3N, so that complicates a bit the interpretation.
JWST would have to shed more light on this.
The thing is that for this guy, this is huge on the sky for James Webb. So, I mean, there were some crazy people who made, I think, a mosaic like this. I don't know how many points they use here, but doing this is unfeasible for James Webb. I mean, you can try to do this in another region farther away.
Maybe just a very compact region.
Yeah, so because, I mean, you know that the overheads of James Webb are crazy, so you need hundreds of points for James Webb.
How many hours did you, for the big map that you showed at the beginning, was Orion, no?
This one?
That one, yes.
So it was a relatively long ALMA project, not the longest, but this is, I think, 12 hours of ALMA. So it's a decent amount. We wanted to do 300 hours, but they don't let us. You know, it's time to dance.
I was looking for the name of the nebula in Messier 33, which is that NGC 604. I don't know, you remember that star-forming region?
Yeah.
It's a huge star-forming region, relatively nearby the Milky Way. just if you were able to discover something like that in an external galaxy.
6334, I think is the one that I was showing.
NGC 604.
Oh, no, 604, no. Maybe, I mean, this is one of these huge examples of huge IMA star forming regions. So the problem is that
if it's in the north.
if it's in the north, you look for ALMA. If
the triangle constellation, so yeah.
No, but I mean, doesn't matter. We have also examples in the south. The issue here is that, like for James Webb, at some point, this is also really time consuming for ALMA. So doing mosaicing with ALMA itself is super tricky. And people have been trying to do this. This requires, I think, the order of 100 hours of ALMA. So it's a large program for ALMA. I mean, it will not be too easy to do.
Any other questions? Here in Zoom, do you have any questions?
I might have a stupid question, but
No, go ahead. No stupid question.
I arrived late, so maybe you said it. But I heard that the main problem now is how to explain the loss of angular momentum when you are forming massive stars. Does this shed some light on, because I guess that's in a smaller scale, right? So the problem is still there, really.
Yeah, in this sense, it's still there. So you will, because you will form, actually, by having flows with a given direction, you already have a really strong angular momentum component in there. So you need to get rid of it. So the way to get rid of angular momentum, not always, but that helps, is to eject outflows, right? So you can disperse your angular momentum in the disk by just ejecting angular momentum via outflows. So this will also, I mean, if you want to see it like it will help you a bit in a sense that, and you have this direction, you have your disk, and then you have already free path to move out the outflow. But this is a much smaller scale, and I will not say much in this. But the problem is still there also for low mass stars. You need to get rid of angular momentum and low mass.
You need a magnetic field for that.
This is what
at the end, you cannot avoid
at the end, but anyway, because then you compact your magnetic field and your magnetic field flux increases, and then is when magnetic field become important. Yes, so you eject it probably with magnetic field, magnetic dynamos.
Okay, so a related point on that is, what do you think about this conveyor belt hypothesis? I think it's called, like, those filaments can collide between them and.
I mean, the conveyor belt idea, for those who don't know it, is that you bring material from outside to inside the cluster. And of course, it depends on which scale you are talking about. But this is the conveyor. This is part of the conveyor belt. So you are. So the cluster here is formed. I mean, we see the late evolution of the cluster, but you are bringing gas and stars actually, because stars are being formed in the process. You are bringing stars from outside the cluster. So you are throwing stars into the cluster from the outside. So this is the way you grow a cluster. Later in later phase, I mean, meaning that we do not know what happened at the beginning of the Orion Nebula cluster. But now you are bringing stars from outside. The gas is outside the cluster, and then you still throw stars in there because of the potential. So the whole system is now dominated by the potential of the combined potential of the cluster and the gas. But basically, you have 2,000 solar masses in stars, and now on the order of 500 in gas, and this is collapsing. So you are bringing, in this sense, the conveyor belt works. The question whether it works also at smaller scales. It works here. You have here these intersections. Maybe also work here. That's an hypothesis that we also want to prove.
Okay, so the whiskers are kind of also part of this mechanism?
If gravity will dominate in this case, yes, that's what we need to prove. But even without the diffuse gas, in between the fibers, you can, when you have a collision, you produce another small potential well that could also help you in the bringing material.
Okay, I think we can stop here. Thank you very much, Álvaro.
Thank you for your time.
Thank you for coming.
Thank you. Thank you for your time. Thank you.